Okay, we are online. Good morning, good afternoon, or good evening. We are starting the second day of our professional training on GNSS, signal processing, and navigation techniques. Uh, uh, I've already put in the chat the link with the agenda and also the materials. You can download the materials from our website. I'm Eduardo Freitas. I'm from Mundo Geo. Mundo Geo is one of the companies that are members of the consortium of the Galileo Information Center Brazil. I thank everyone that is already connected in this webinar, and also thank the presence of the speakers, Adria and Felix. Well, I think we can start. We will have a first period and then a Q&A sessions before the break. And then after the break, we have the second part of the presentation, and then by the end, the final Q&A session. Adria and Felix, when you like, you can start and also start sharing your screen. Good morning or good afternoon.
Good morning. I will share my screen and then start. Okay, there it is. Good morning, everybody. So today we're going to start the 2 days of looking into signals and signal properties of GNSS and signal processing. We will, as Adrian mentioned yesterday, we will work up to the tracking and up to the generation of the estimates of time delay, phase and Doppler estimates for each satellite, and then Adrian will take over using these measurements in the positioning. And this they will continue at Adrian and Jaume. They will continue on Thursday and Friday with the positioning. So let's start looking into the structure of the signal and how can we use the signal for ranging today. So here's the outline. So we will discuss what's multiple access and multiple access schemes. We will learn then, secondly, that what is a spread spectrum signal. We will then I will introduce the processing gain, and we can discuss a little bit the interference robustness of spread spectrum signals. And then in the end, we have already a glimpse into time delay estimation, how this can be done. And we will discuss this more profoundly later tomorrow afternoon. Yeah, so what is multiple access? So several satellites need to share the same transmission medium and broadcast to the GNSS users to enable positioning. The satellites need to share the transmission medium such that the GNSS users can separate the different satellites, perform ranging, and also receive the navigation data, which is very important for the positioning then later. The satellites need to share the available bandwidth by using channel access or what's called multiple access techniques, because they need to share somehow this bandwidth. Multiple access techniques have the aim to ensure that the signals of the different satellites will be separated or even orthogonal. In general, there are 3 basic MA techniques. So we have time division multiple access, TDMA, frequency division multiple access, FDMA, and code division multiple access, CDMA. So how can we explain these 3 basic schemes? There's a 4th one, which is called spatial or space division multiple access, but we will not cover this here. Then you need multiple antennas on both sides, on the transmitter side and the receiver side, or at least on the receiver side. As this is not given for most of the GNSS receivers, we will focus here on these 3 schemes. So for time division multiple axis, we have the axis time, frequency. In all these three pictures, we have the axis time, frequency, and code. And you can see here in time division multiple axis, we have the different users transmitting. This is shown here by these squares in different gray shades. So they transmit in different time slots. They use the complete frequency and they use all the same code or no code at all. In frequency division multiple axis, the users, they transmit in different frequency chunks or sub bands, frequency, sub bands in the complete total bandwidth, and they are transmitting all the time, but separated in different sub bands. And then there has code division multiple axis, where we have the users transmit using the complete bandwidth and all the time. They broadcast all the time, and they're using different codes to separate the different transmissions, or in our case, the different users, the channel users, and they're the satellites. In principle, each of these techniques can achieve the same aggregate spectral efficiency. So they achieve the same symbol rate per user of the channel per satellite. The number of users per satellite, so the number of users per channel, the satellites are the users, so the same number of satellites. The same sum symbol rate. And these basic MA techniques can also be combined to form hybrid combinations. So we can, for example, combine frequency division, time division, multiple axis. Or we can have frequency division, code division, multiple axis. Or any other of these hybrid forms. For GNSS, there's certain important facts about the choice for the MA scheme. So the number of in-view users or satellites is quite low, so around 12 per system in maximum that are visible for a user at any location on Earth. The data transmission demands in general do not play a prominent role, so the data that is transmitted is not a big amount. So we're not talking about streaming a video from a GNSS satellite. So this is very low in the current. For example, in the GPS-CA code, we have 50 Hertz data rate. So it takes very long to receive only a little bit of data, but the data is not so much. We receive from the satellite only ephemeris, so the position of the satellite or at least parameters to calculate the position of the satellite. We receive parameters for correcting its clock offset. We receive parameters for the troposphere and the ionosphere model. So there are some parameters that we are receiving, but it's not a big amount of data in general. And mainly other performance measures have to be considered when choosing the appropriate MA technique for GNSS. So this is different from communications. So signal design properties for GNSS are synchronization accuracy. So we want to synchronize our receiver with the time, with the signal that is transmitted from the satellite. Synchronization here then means estimation of time delay, Doppler, and phase. Synchronization robustness is important for us. We want to robustly track these parameters because with the measurement of the time delay, we will generate pseudo range and later range in the positioning and the position solution. Also with the phase measurement, and Adrian later this week will explain you how this works, and Jaume, they both will explain you how this works. The phase measurements are also used in the positioning. So both of these measurements are very important. The Doppler is also used in the positioning and is as an important parameter for the synchronization also. Inter-system multiple access interference. There is interference, as we have seen. For example, we have no interference in the TDMA and FDMA schemes, but we have this interference in the CDMA scheme, for example. And then there's so we need to have multiple system access interference, inter-system multiple access interference. We will call this MAR, or spectral separation. This means the separation between the different systems in band, because we have already seen yesterday most of the GNSS signals they share systems they share the same. Most of the GNSS, they share the same bands. So we have to make sure that the interference between these systems is low. Also, the intra-system multiple access interference, MAA, this is the interference between the different satellites of the same GNSS, has to be low. Yeah, and in general, we also would like to have some interference robustness to, for example, low bandwidth interference from other systems, or from, if we talk about jamming already, then people who try to harm us. This is also important. And then for one of the more important parameters then for the positioning and the accuracy or robustness of synchronization is also multipath performance. The signal shape has influence on this performance, and also the autocorrelation function of the signal itself. And there's several more properties that are interesting for signal design for GNSS. Most GNSS, GPS, Galileo, and Beidou, use direct sequence CDMA, so DS-CDMA, so a code division multiple access. So the satellites have different codes. Each satellite uses a different code for transmitting its signal. Spectral separation between different GNSS in the same frequency band can be achieved by usage of different modulation schemes or chip pulse shapes. And we see this today in the afternoon, today in the morning. And then we end up with a frequency division, code division multiple access. So this is the scheme that most of the GNSS use. There is the Russian system GLONASS uses a CD-FDMA approach because it has the same spreading sequence or the same code for all the satellites, but the satellites use different subbands of the total bandwidth. Yeah, here we have as an example to illustrate the FD-CDMA approach. We have the GPS-CA code signal in the spectrum, so the normalized power spectral density in dB watt per hertz. For the carrier frequency L1 or E1, and this is 1.57542 gigahertz. And this is here given at 0. And this is the carrier frequency. So this is the signal in baseband, and then the calculation of the normalized power spectral density of the different signals. So we have the GPS-CA code signal in black. That's the signal that you use today in your phone mostly. Then there is a modernized GPS and Galileo open service signal. So the modernized GPS signal is already available, I think, on 2 or 3 satellites, and the Galileo open service is available on all the Galileo satellites. Then we have the new GPS military service. It's called M-Code, and the Galileo public regulated service, which is also the military service. And you can see that the designers of the signals, they have chosen to choose different, or they have chosen different modulation schemes, because you can see that the green, for example, the green spectrum is not really overlapping with all the other signals. So the main part of the power is located at a part of the band where there's no main part of the other, or main power, or not a lot of power of the other signals. The same thing you can very drastically see also with the Galileo PRS service. So you have most of the power very at higher frequencies, and you have nearly no power in the center. of the band. However, GPS-CA code signal is located exactly at the center of the band, but it falls rapid. The power is decreasing rapidly to the edges. And then you can even see that GPS, the modernized GPS, L1C it's called, the signal is called L1C. Galileo and the Galileo Open Service, they are spectrally a little bit separated from the GPS-CA code because their main lobes of the spectrum are a little bit shifted away from the carrier. And this is how the signals implement the FD-CDMA approach. So to be spectrally separated in band, and then all the satellites and of the different systems are separated by a code, and the systems have a CDMA approach for the multiple access. Yeah, how can we now use these spread spectrum signals, these direct sequence CDMA signals? So the received DS-CDMA or the CD-FDMA baseband signal, it's a general form that we use here. We can write this here as x of t of p squared times gt minus tau, c of t minus tau plus n of t, where p is the signal power, C of t is the pseudo-random spreading sequence. That's the code sequence of the different satellites. And for the CD-FDMA, I told you that the satellites use all the same code, but they use a code to spread in the subband, to spread the signal in the subband. But they're spectrally separated through that they use different parts of the band. However, we will focus mostly on the DS-CDMA systems in this professional training. Yeah, then we also have the time delay tau, which is in fact this is the time delay of the experienced in the receiver with respect to a origin or a T0 that the receiver sets with his reference clock. And then we have the binary navigation data, which is here given by G of t. So it's and n is usually white Gaussian noise with power spectral density of n0 divided by 2. So the PR sequence then can be further detailed into a sum here over dm, where dm and convolved with a Dirac train and chip pulse shape. So PT is the chip pulse shape, which is not necessarily restricted to be time limited to only one chip interval. Then we have TC is the chip duration. The PR sequence with so we have the sequence is also binary, as we can see. So we have the symbols or the bits of the sequence. They are multiplied with the Dirac train. So this is a delta Dirac function here, the delta. And then the star means convolution with the chip pulse shape. And then we can write this also as a superposition of delayed versions of the chip pulse shape multiplied with the code bits. And the duration TD of the PR sequence is ND times TC, where ND are the number of chips. So one of the bits of the code sequence is called chip. So the number of chips of the PR sequence is ND. Yeah, so the PR sequence can be assumed simplified to be a zero mean. So the code bits, the expectation of all the code bits over M is 0, and wide sense cyclostationary sequence. So with the properties that the expectation of dm dl conjugate is equivalent to the autocorrelation function of the sequence at the position M L minus M, and the autocorrelation function M L minus M is cyclostationary, so it is the same, so it's repeating over it's repeating over the correlations. So we assume that the sequence is normalized to 1. So we have the C times C conjugate, and then the integral over the duration of the sequence divided by the duration of the sequence is 1. And then we can, with Parseval's theorem, we can also write this in a frequency domain. So phi of C is the power spectral density of the sequence of C of t, and this is assumed to be 1. So the autocorrelation function of C of t can be given as the duration of the 1 over the td, so the duration of the sequence, and then the integral from minus td half to d td half over the multiplication of C of t times C conjugate t plus epsilon. So that's autocorrelation here, and then we can rewrite this into the P of f is the Fourier transform of the chip pulse shape. So we take the absolute square of that, and then phi of d, which is the PSD of the sequence, times e to the j 2 pi f epsilon. So this is Wiener-Khinchin theorem here. And then we have we can assume that if phi of d is equal to 1, that the autocorrelation function is only given by the chip pulse shape, the Fourier transform of the chip pulse shape. If the chip pulse shape is not, and we assume that here the chip pulse shape is normalized to 1, which is given in all the signal model that I introduced so far, and the power spectral density of the sequence dm is assumed to be random. So the code sequence is not only pseudo-random, but if it's random, then the power spectral density is equal to 1. And then we can have this, so with this assumption holds here. In practice, this model is very, very close to the reality. So the model of this autocorrelation function is used widely in the literature and for assessment of performance. So the autocorrelation function in the end is only defined by the chip pulse shape of the sequence, if the sequence can be assumed not only pseudo-random, but random. Based on the interesting result, we can conclude the problem of optimizing cross-correlation, autocorrelation properties of the PR sequence can be treated separately as two different problems. So optimization of the wide sense cyclostationary sequence and their properties. So this is one field of research, and it's a very important task in designing a GNSS. And then secondly, optimization of the chip pulse shape, because this defines the shape, as we have seen, the shape of the autocorrelation function of the signal. And later we will see during the course that this shape of the autocorrelation function defines the robustness of the synchronization algorithms. So and also the accuracy of these algorithms. So it's a very important part of the signal, so the design of chip pulse shapes. Easy analysis and understanding of the properties of chip pulse shapes so P of t and PR sequence is given by this separation into two problems. And now we can understand what happens with these sequences in the receiver. We have just seen what is autocorrelation, and the receiver performs correlation with a period of TD using a replica signal based on a model. So in order to separate the different satellites, and we see this then on the next slide, he needs to do this. But in general, he uses this cold replica. Here in our formula, he just uses C of t minus tau. So he knows exactly the time delay already, is already estimated, and you can perform correlation by this integral here. And you also have to do this for the noise. So you have the received signal multiplied by c of t minus tau. You take the integral over one period td. Here, this is the kth period, while k runs from 0 to capital K. And you also have to do this for the noise. So this is what the receiver performs before doing measurements. And this ends up into the power, because as you maybe remember, c of t times c of t and the integral over one period, we assume to be 1. So it's normalized to 1, and then we arrive here at the result of this integral is just the power, the square root of the power times the navigation message bit at the time instant k in this integral, during that integral, and then we have the noise, and I call this here noise brief. This symbol here is brief. So n brief at k. So where k runs from 0 to k minus 1, and g of k is the binary message that is not changing during one of these intervals here. The power of the signal and the noise after the spreading then can be given as, so the expectation of the absolute value square of the square root of p times g of k is given by p then. And we can also calculate the expectation, so the variance of the noise, as the noise is zero mean. This is the variance, so we have n brief, absolute value square, and then the expectation, and this is sigma brief square of n, so for noise, and this is equivalent to n0, so which is the power spectral density of the noise, n0 half divided by td. Yeah, considering now the reception of n, so this here was for one satellite, so correlation for one satellite. So now let's see what happens if we receive several satellites. So considering the reception of n satellites for each, for either a DS-CDMA or a CDF-DMA system, we can now write. So we have again the correlation with the signal of interest. So we correlate with the sequence C here, and there's also a number of satellites with I from 1 to n sat minus 1 satellites. So all the other satellites that we are receiving, and they have the sequences CI. So each one has a different one. We're also correlating this, so multiplying this with the sequence C of the first of the satellite of interest, and we can see that these, based on the sequence properties of the pseudo-random sequences or the spreading sequences C, the code C, these integrals are all zero. So the correlation between the sequence of the satellite of interest here and all the other satellites is approximately zero. It's not exactly zero because we already talked about this. There is multiple axis interference, but it is very small. So here on this slide, we say it's approximately zero. In reality, this is something that you have to take into account in your performance, and especially in the design of the signals. But I mean, the design task of designing signals for GNSS is to keep this cross correlation among the different satellites as low as possible. So that's why we can here simplified say that this is very close to zero. And then we have the noise also. And this is approximately then, again, the signal of the satellite of interest. So it's, again, the power of the satellite of interest squared times the message data bit at the instant k plus n brevi, again, this noise after despreading. So here we have seen now mathematically how the satellites are separated with respect to using or with respect to their code sequences. In case of direct sequence CDMA, the satellites are separated using different PR sequences, while in case, and I'm repeating this here, of CDFDMA, in case of the GLONASS system, the signals are separated spectrally. All satellites use the same PR sequence. Then this equation would be different, because then the CIs would be different here as well from the Cs, because they are transmitted in different subbands. Yeah, so now we have understood what's correlation, we have understood how can we separate the different satellites in a DS-CDMA or CD-FDMA approach. Now let's develop a just discrete signal model. And to work with during the course. In the receiver, the observations are collected at n time instances in k periods. So we have usually we have an antenna. We have also some down conversion to baseband, so demodulation from the carrier frequency, and then we have also some kind of digitalization or quantization of the signal, and this is done at n at time. I collected at n time. This is what I mean here with collected at n time instances. So the signal is sampled at n time instances in k periods, and thus we can write then the received signal x. K times capital N plus N, and this is equivalent to the continuous version of the signal at Kn plus N times Ts, and Ts is what's called the sampling duration, and this is then 1/2 times B, and B is the bandwidth of the signal, the one-sided bandwidth of the signal. A simplified model of the received baseband signal after sampling can be given by this. So this is the baseband model, or the simplified receiving model that we will use for this course. So we have here on the far left, we have the antenna. Then after the antenna, in reality, we have some low noise amplifiers, some band pass filtering, and so on. But here in the simplified model, all the effects of the amplifiers and filters, they're inside this filter H of L. We have then the noise, because the noise is not received by the receiver. It is generated mainly inside the receiver by the antenna and the low noise amplifier. So the noise is generated before all these filtering happens, and the filtering in the receiver is all modeled here by this filter HL. After that, we have a sampling at time instances. T equals K capital N plus N times Ts. So we have these for each period K, we have N capital N samples. And after that, we have a sampled version of the signal. So we have sampled time instances of the signal with a certain duration. And here we will, for the simplified model, we will also use the simplified filtering, because the filter is just a low pass, an ideal low pass filter. So HL of t is equal to 2b sinus 2 pi bt divided by 2 pi bt. And then the Fourier transform of this filter is, we can see that inside the bandwidth of the signal, which is here also the bandwidth of the filter, has a response of 1 and has 0 outside of this bandwidth. So it's very simplified model. But we have some band limitation, also some band limitation of the noise, but we can show that the noise with this ideal low pass filter, the noise when it's passing through the filter, and then we sample exactly with a duration Ts equals 1/2b, the noise, the sampled noise is still white Gaussian and has no time correlation. So the noise statistics is preserved also by the filtering and the sampling in this special case when we have an ideal low-pass filter. So the duration of the chip of the sequences of all the chips in the sequence is TED, as you remember, and then we can also give here the relation to NTS because we have n samples per period. And then this can be also given by n divided by 2b, as TS was 1 over 2b. We will need this relation later. We can also write now the signal as we have discretized it, we can now form a vector signal. So the vector x of k, which gives us, as you can see here, n samples. They are organized in this vector, or they're included in this vector, capital N samples. So from kn ts up to kn plus n minus 1 ts in time, we have these samples. This at the end of the vector here, this means transpose. So this we have written here a row vector, and the transpose makes it a column vector. So in the model above, the vector definitions on this slide, we have all column vectors. So it's the column vector for period k is equivalent to the square root of the power times the symbol at the time instant k times a vector k parameterized by tau. That's the sampled sequence in our case, plus the noise also sampled. And the dimension, yeah, as I said, this vector x here is a column vector, so it had n rows is real and has n rows times in this model here it's real, and it has n times one n rows and one column. So we assume that the sequence it can be normalized, or let's say the L2 norm of the sequence is equal to 1, equal to n, while in general this is not given for all time delays. In the case of for example, GPS CA code signal with PR sequences with a bandwidth of larger than 1.023 megahertz. This is approximately given that for any time delay, the norm of the signal is approximately n. This is important for our preceding models, and additionally, n is larger. And this is always the case in all the cases that we will look into here. The number of samples is larger than the number of chips, and the number of samples and chips, they are an integer. They have an integer. So the n divided by nd is an integer. So we can then we can drop the k, because then the sequence is just repeating for each period. And it is still delayed by tau. Yeah, now the autocorrelation function of the PR sequence can be given as E of epsilon now can be given as 1 over n C transposed delayed 0 times C of epsilon. So this now is our correlation, how we can write correlation in discrete. You see here that the vector notation avoids writing the sums instead of the integral. So we have now a vector, because this is a row vector times a column vector, and this creates like the sum of all the different entities of the vectors. So multiplying the first element of C of 0 times the first element of C of epsilon, plus multiplying the second element of C of 0 times C of epsilon, and so on. So this is correlation, while as we have assumed also in the continuous for the continuous signal that the autocorrelation is normalized to 1 if the delays match of the two sequences. Yeah, the receiver performs correlation with a period of NTS minimum using a replica signal based on a model. So it assumes it has a specification. Usually you can open the specification of the different GNSS. So you They're called signal ICDs, interface control documents, signal in space, signal in space, interface control documents. And there you find this model that most of the receivers use. You can further detail the model based on the reality of your, or the real reception receiving characteristics of the receiver, and be aware that also the transmission of the signals, so the signals transmitted from each satellite are a little bit different, because each satellite has a different characteristic also in its transmitter. So, and you can refine this model, but in principle, most of the receivers, they rely on the model from the SysICD. In case the time delay tau is known and cross-correlation with other satellites can be neglected, as we did before, we can now write again here cross-correlation with the received signal. And as we will assume again that the correlation with the other satellites is 0. So this is a convenient way of writing this now in discrete form. So we have 1 over n c transposed of tau multiplied with x of k, and then we can see that we can split this up into the signal part and the noise part, and in the end we arrive at again the signal power square, the square root of the signal power times g of k, which is the symbol received of the navigation message received at time instant k, plus 1 over n transpose 1 over n c transposed tau times the noise. Also, this was in this is then our n breve at k. Yeah, so this was introduction into correlation, cross-correlation, how to separate the signals of a DS-CDMA and also of an CD-FDMA scheme. So for GPS Galileo Beidou in the DS-CDMA case and GLONASS in the CD-FDMA case. We can now talk about the spreading gain and also have a quick look into what is how we can deal with interference. I'm just also looking at the clock so that we have time for our questions or for questions at the end. The multiplication of the navigation data sequence G of t with the much faster oscillating PR sequence C of t introduces a spreading of the spectrum of the navigation data sequence of the factor S. So this is the spreading factor S, and this is equivalent to the ratio of the duration of the sequence divided by the duration of one chip of the sequence, because this is kind of how much you enhance the oscillation of the signal by multiplying the message with the much faster oscillating PR sequence. So S is often called spreading factor. In general, as we have seen, we have many chips per sequence, so the duration of the chips is much smaller than the duration of the sequence, and the spread signal thus can be hidden below the noise in case the maximum value of the PSD of the noise is n over 2 is larger than the maximum value of the PSD of the spreading signal, phi of c. This is the original, let's say, one of the original ideas also of direct sequence CDMA signals. One of the original ideas was to hide the signal before correlation below the noise floor, and after correlation the signal. So if you know the sequence and you can correlate the incoming sequence with this the incoming signal with this sequence, you can then see the signal above the noise floor. And this was one of the original ideas also of using spread spectrum signals, and this is also the because when you this is also the reason when you if you connect an oscilloscope or a spectrum analyzer after the antenna in your receiver, you see not only the noise, So there's only noise. The signals are all buried below the noise. Sometimes you can see, depending on the power, the low noise power amplifiers that you use, you can see a little bump in the center of around where all the signals of all satellites are adding up. So you can see maybe a little bump in the spectrum where all the signals have the strongest power and they all sum up. But in principle, if the low noise amplifier is not so strong, you can see nothing but noise. So your spectrum analyzer shows you just noise, which is kind of a flat. It shows a flat spectrum, a power spectral density in the complete band. So you see nothing from the signals. You cannot see them. There's a lot of analysis also done with high gain antennas. In at least I know in Europe, the German Aerospace Center is doing this. They have an antenna with like 50 dB gain, and then you can lift the signals even before correlation above the noise level. So your noise level is very low because the antenna has such a huge gain towards the satellite. And then you can also look into the structure of the spread signals. But in principle, in a common GNSS receiver, you cannot look into the spread signal. You can only work with the correlation, because when you correlate, you sum up the power over some time, and so you average over time, and as you know the sequence, this correlation will kind of lift the signal after correlation up above the noise level. And we will see on this on the following slides mathematically how this is playing out. Yeah, this is graphically already shown what I mean. So we have the power spectral density of the code, which is very flat here in the it's the solid line, and this is over the frequency, and FC is here the carrier frequency, and then we have phi g, which is the power spectral density of the navigation data message. So we are multiplying the data message. We're multiplying the data message with C of t, and then we end up with the power spectral density, as we have seen already, of phi of c, of the signal, which has then the power spectral density phi of c. If we then perform correlation, the signal after correlation has the power spectral density of phi of g. And if you assume now that the noise is maybe somewhere here in the middle, let's use the whiteboard here. So for example, if the noise floor is then here, so let's say that this is, oh God, N0. I will practice this over this next days. Yeah, so if this is N0 half, you can see what I've just said. So you can see that the signal can rise, the power spectral density of the signal can rise above the noise floor, so that you can see this really in your spectrum analyzer, the signal after correlation. But before correlation, the power spectral density is below the noise floor and is not observable with an oscilloscope or power spectral density estimation device. Yeah. So let's have a look into the mathematics on this. So, and this is then will lead us to the definition of the processing gain. So the signal to noise ratio, so the power ratio of the signal power to the noise power before the correlation, we can calculate this. That's the expectation of the L2 norm square of the signal, which is then the square root of the power p of the signal times g of k times the vector of delayed vector of the spreading sequence. And we take the L2 norm of this. This takes all the entries of this is a vector then inside this norm, and we take all the entries of the vector, take the square of each element and sum them all up. This is the norm, the L2 square norm. And then we take the of that, and this is p, because the norm of c, as we have seen already, the norm of c transpose times c divided by n is 1. G of k is G of k is 1 only, or -1, and when we take the square of this is in the squaring process, this doesn't play a role. So this is n times, so we see that and then the expectation is dividing by n, so we have just the square root of p and then the square of that n times, and then the expectation over time, so this is p then. And the noise, we have this noise power, so the variance of the noise, so this is sigma n square, and we can write this as n0b here. So that's the signal to noise ratio, and remember b was the one-sided bandwidth of the signal. So that's the signal to noise ratio before correlation. So let's now calculate the signal to noise ratio after despreading or correlation. There's always these two words in GNSS. Most people use more before correlation, after correlation. In communications or in the or let's say in the literature that defines the origins of direct sequence CDMA systems, they talk more about spread signals. So this is before correlation, and after correlation they call despreading. So they use the term despreading for correlating. Yeah. So yeah, we can also calculate after correlation. So then remember, we have multiplied our signal with c of tau, with the vector, and we have divided by n. That was our definition of correlation. Now we can take also the absolute value of that, because this is now for each period. This is a scalar. So for each period k, and then we calculate the expectation over k. And this is again p. So this is again p, and then we have in the denominator, we have 1 over c transpose times n. This is also a scalar for each period k, and then we calculate the expectation over many k's. And the only statistical, let's say, because the C of t is here is pseudo-random, but it's a deterministic. It's a vector that it's defined by the sequence. So we can build only the we can only have to calculate the expectation of nkn, and this is Hermitian here. N Hermitian. Hermitian is the transpose conjugate of the vector, and this is an identity because the noise is has no correlation in time here, and so for the noise realization, only the noise is correlated if it's not delayed. So we have uncorrelated noise, and then this I of n here is an identity matrix. So you have in the diagonal of the matrix all ones, and the rest of the matrix is filled up with zeros. And if we multiply an identity with a vector, this is the vector again. So the noise, as we can see in the denominator, we have then C of transpose times C conjugate, and this was 1. So 1 over n C transpose times C conjugate is 1. Then we end up in the denominator here with sigma n squared divided by n, and we can also put the n up in the numerator. So we have p times n divided by sigma n squared. Now we can go back to our some slides back. We had some formulas how to express n, and now we can express n here in terms of the sampling rate and the duration. So n is equal to td times 2b. And from above, we also know, from above of the slide here, we also know that sigma n squared is n0 times b. We can fill that in, then the b disappears because we have a numerator and denominator, a multiplication with b. And then we have p divided by n0. And we will define bd now, and bd is b divided by td. And then the bandwidth of the navigation message signal. And then this is p over sigma brief squared of n. So this is the signal to noise ratio. First we calculated before correlation, now after correlation, and we can see already what's the relation here. The relation is a factor of n, right? If we look into the second row of the derivation of the signal to noise ratio after the spreading SNRD, we can see there it's equivalent to p times n over sigma n squared. And the signal to noise ratio before correlation, if we look up in the first equation here on the slide, we have p divided by sigma n squared. So it's a factor of n that the signal to noise ratio is increased. What does this mean? This means that the signal before correlation has, so the signal, either the signal power is larger by a factor of n after spreading, and the noise power stays the same, or it means that the signal power stays the same and the noise power is reduced by a factor of n. Yeah, so this means, this is effectively the second is a better interpretation of it. So the noise power is reduced by a factor of n, and this is why now we have a signal to noise ratio which is larger by a factor of n, and this is the effect that we could see, that the spectrum of the signal is rising above the noise floor. The relation now between the signal to noise ratio after and before the spreading can be given, so SNRD is P divided by N0BD, and this is PB divided by N0B. We can just multiply on top and below again, and then we see that this is the signal to noise ratio before the spreading, so before correlation, SNRS times a factor G. And this factor G now is the relation between the bandwidth of the spreading sequence divided by the bandwidth of the navigation message, or the message signal, that we are multiplying with a much faster oscillating spreading sequence. Now there is also a relation to the spreading factor S, and this relation R here is, or this factor, this scalar R is relating to the time bandwidth product of the two signals. So there is a time bandwidth product of the signal of the spreading or the spreading sequence, so the code sequence, which is B times TC, and then there's a time bandwidth product of the navigation message sequence, which is BD times TD. And it depends on the design of the signal what these time bandwidth products are, and this defines the factor R here. But there's a relation. But in principle, we can say that the spreading factor is as we define it, is the relation between TD divided by TC, and the processing gain is the relation between the ratio of the two bandwidths of the signal. And processing gain is lifting up the signal above the noise floor, so that we can detect the message bits by it. As you already have seen, I will finish this, and then I will give some additional information. So the processing gain G is a result of the change of the noise bandwidth and the resulting noise power. The spreading factor S describes the spreading of G of t by multiplication with C of t, and the processing gain describes the gain in SNR after the spreading. So this is the difference of the two. You already have seen that this processing gain, the maximum was only achieved if the delay is known, and we will now in the remaining couple of slides we will discuss how the time delay is estimated, and it's also estimated using correlation, looking at the at the gain in SNR, more or less, of the signal. This is used also to estimate time delay, because where this is maximum, the time delay is the correct time delay of the signal, right? So if we find the time delay that is the correct one, as received from the signal of the satellite, or as incident in the signal of the satellite, this correlation is maximum, and then also the processing gain is maximum. So just a few words on interference, as we have calculated already SNR before correlation, after correlation, the signal to interference plus noise ratio, the SINR, before despreading in case of additional interference with power J. And this is the special case of an uniformly distributed jammer across the band B, can be given as. So we have then not only the noise in our ratio of powers, but we have an additional interference that we have to add to the noise here. So this is noise plus interference in the denominator. So it's Bn0 plus J, and in the denominator we have P. The SINR after the spreading then is P divided by Bn0 plus Bd divided by Bj. So we can reformulate this, and we arrive at the equation P divided by Bdn plus J divided by G. So this is the SNR after despreading. And we can see that the noise power is the same, and the interference power is reduced by the spreading gain. And that's this states, so for broadband interference, the SINR increase after despreading is dependent on the processing gain. And the system design can incorporate certain interference robustness, yeah, because if we design a system with a large processing gain, so with a long spreading sequence and a large bandwidth of this spreading sequence using for this spreading signal, we achieve a high processing gain, and thus we can, as you can see, the power of the interferer after despreading is J divided by G. So the higher this processing gain, the less the power of the interference after despreading or correlation. So for narrowband or partial band interference, I just mentioned this here, C of T spreads the jamming signal so that it appears as wideband Gaussian noise at the output of the correlator. So this is interesting if we have, let's say, a sinusoid that we receive additionally to our satellite signal. By the multiplication of the sinusoid with C of T spreads the sinusoid across the band, right? So the sinusoid has two Dirac pulses as a spectrum, and then these two Dirac pulses are spread
Hello, Felix. Do you hear me? We cannot hear you.
Hello?
Just
Yeah.
one. When
Okay.
now it's perfect. Thank you. Maybe 1 minute. We lost your
Oh,
audio.
okay. So I
If
go back
you
here.
could please. Go back and start again.
Yeah.
Okay, thank you.
So I just summed this. I'm very sorry for this. I have Yeah, I will just sum up this slide again. So we have discussed the signal to noise. Here it's shown the signal to interference plus noise ratio before correlation and after correlation. And we see this for this broadband interference case, where J is the power of an uniformly distributed interference across the complete band of the signal. So before despreading, we can see here the signal to noise ratio. So in the denominator, we have a large contribution of the noise power of the interference power. After despreading, this contribution of the interference power J is dependent on the processing gain. So if we have a large processing gain, and this can be achieved by the design of the system. How can we achieve this? We can use a long, or design a long spreading sequence with a large bandwidth. Or let's say a large bandwidth of the sequence, because the spreading gain is dependent on the bandwidth of the spreading sequence. So the larger the band of the sequence, the larger the processing gain becomes, and as we can see here, the better the protection against broadband interference becomes. In this final bullet here, so this is what I mean here with the second bullet. That means system design can incorporate certain interference robustness. I mean, this is not perfect because if the interference power gets very, very strong compared to the processing gain, then also after despreading, we have still significant disturbance of the interference, and this will harm our receiver still, even after correlation. On the other side, interesting, and this is the last bullet that I show here, for narrowband or partial band interference, which is, for example, a sinusoid that we receive in band as an interference, the interference is spread by the multiplication with the spreading sequence. Remember, correlation is first the multiplication with the spreading sequence with the known time delay, or with a probing time delay, and is then spreading this sinusoid in the band while it is focusing the power spectral density of the satellite signal. So what you can see here is like a spreading effect of the interference. So the interference will disappear below the noise floor, and the signal of interest is appearing above the noise floor. So this also introduces some robustness against interference. Again, if the power of the interference is so large that even after the spreading, it appears above the noise floor, it will still harm in general, will still harm our receiver. So let's move on to these last couple of slides, and we will have what time delay is done. And we'll need this later in the course. So let's assume here that we only take from our signal x the first period, so the period at 0. So we call that then the vector x. This makes it a little bit easier to write things. And let us assume a random variable x has a multivariate Gaussian probability density function, PDF, and is parameterized by the parameter tau. So, and thus we get, so this is the probability density function then of this multivariate Gaussian x, and the the likelihood function with respect to the parameter tau then can be given as, so the likelihood L of x parameterized by tau is equivalent to the probability density function. So the difference between likelihood and probability density function, they seem the same, but it's like looking at the same thing from different angles. So the likelihood x of tau is a function of the parameter tau, which is to be estimated at a given realization of the random variable x. And this given realization is then our received signal, and we're trying to match to the signal the tau that fits best to the signal. The PDF px of x parameterized by tau is a function of the realization of the random variable x for a given or fixed value of the parameter tau. For example, if you want to generate realizations of the random variable x, you can use the PDF with a certain tau and then generate these random variables according to the probability density function. So that's the difference between likelihood and probability density functions. In the following, we will use the likelihood because this matches our case. We have a realization of a random variable that we have received. This is the signal, which is modeled as a multivariate Gaussian. We are trying to match the parameter tau as best as possible to, and we will do this on the next slide, to maximize likelihood. So now the maximum likelihood estimator, so we're trying to maximize this likelihood now with respect to tau. So we have received a realization of the random variable x. We're trying to find the tau that matches best to this received realization of the random variable x. So this is just maximizing the likelihood with respect to tau. We can also maximize the the natural logarithm or logarithm of this likelihood, because a logarithm is a monotonic function. If we maximize L, we can also maximize L of logarithm of L. This is the same. So, and this helps us a little bit because, as you see here, we have the expectation, the exponential function. If we apply the not natural logarithm, for example, to the PDF or the likelihood, this helps us in the formulation of the problem. So the maximum likelihood estimator is asymptotically unbiased, so for large n, and efficient, which means that it achieves the Cramer-Rao lower bound, which can be calculated as a minimum, as the minimum standard deviation of the estimation error for a given signal and signal characteristic. When further deriving the estimator we get. So let's plug this in now. So we have argmax, and we plug here in our likelihood. We take the natural logarithm in our case, which is given here by log, and then we arrive at log 1 minus log, and then of 2 pi sigma n squared to the power of n divided by 2 minus 1 over 2 sigma n squared, and then the L2 square norm of x minus, and this is then the model. So here we are fitting, in this part we are trying to fit our signal model, which is the square root of p times c of tau for any tau that maximizes this fit and thus minimizes this and maximizes this norm here. As the first two terms, they don't depend on tau, we can just drop them in the maximization, because when we maximize tau, they will not change, right? So we can just drop it, and then we can further develop the last term. So this is then minus x, the L2 norm of x, plus 2 times the square root of p x transpose c of tau minus p, and then the L2 norm of c of tau. And remember, we had the L2 norm of c of tau is not changing with respect to tau in our case, so this is n. So the last term and the first term, they also don't depend on tau in this formulation. We can also drop them, and in the end, we arrive at the estimate of tau is equivalent to the maximization of the cross correlation. And we already have assumed this because we have seen that correlation is maximum when the two signals match as much as possible, and they are correlation is minimum when they are uncorrelated, so it's then zero even. And this is what we also use here to find the time delay. So we're searching through all the time delays that are possible to find the time delay that matches best to our signal that we have received. So the realization of our random variable x. And we can call this here also the cost function j of tau, this cross correlation. So in practice, we will use a delay lock loop in the receiver, and we will later see in the course what this means. And we apply a gradient ascent method to solve this problem. A gradient ascent method here means that we use the time delay of a previous period k minus 1 plus mu, which is called step size, and then the derivative of the cost function of our maximum likelihood estimator at the time, or at the instant, or at the time, using the time delay of the previous time instant. And this produces an estimate iteratively. If we iteratively run this, the process should arrive at the maximum, or at the true time delay, or at a very good estimate for the true time delay. The derivation now can be approximated using the central difference coefficient, or quotient, central difference quotient of length 2d. So we can approximate the derivative with respect to tau in the second term of the first equation, and write it as the central difference quotient of length 2d. So mu is divided by 2d, and then we take a value of the cost function at plus delta and the value of the cost function at minus delta. And this approximates the derivative. Then we can plug in the formulation of the cost function again, which is the cross correlation. And we see what happens. We can take the cross correlation with the signal at a time instant plus delta and a time instant minus delta. So tau hat k minus 1 plus delta, or tau hat k minus 1 minus delta. And this is how we will find our time delay, because in our receiver then, and then we will form a stochastic version of this gradient ascent method, considering successive periods of k. The difference between the second equation and the last one is only that we have then x transpose of k minus 1. So we use the data received at the time instant k minus 1, take the cross correlation at delta at c tau hat with c tau hat k minus 1 plus delta and c tau hat k minus 1 minus delta. So we perform two correlations in the receiver in order to approximate this derivative. So we calculate two correlations. The output of the two correlations, we build the difference, multiply with the step size, which is the design parameter in this method, divided by 2 delta, and with the previous estimate of our time delay, we generate a new time delay estimate. And this is what we can do for all the periods. And with this manner, and this is the basic functionality of a delay loop, we arrive at a feedback system that provides us with time delay estimates. In the receiver, this is usually called then the function here is called the discriminator. So this the cross-correlation function difference here. This is called the discriminator, and it's also we can define the so-called discriminator S curve, S of epsilon, which is the autocorrelation function of the signal. We assume here that the model of our signal matches perfectly to the received signal at the time instant epsilon minus delta minus RC of epsilon plus delta, and we can also write this in our discrete model. And this is graphically showing what's happening. So we calculate, and this is the correlation at the time instant where we use minus delta is in the receiver called early correlation, and in the receiver we calculate also the correlation at plus delta using the estimate of the time delay estimate from the last period, and this is then called late. And we take early minus late. And this is now shown here with respect to the autocorrelation function of the signal. What happens when we calculate these correlations over time, over the periods k. So at k minus 1, we have early and late here on the left-hand side of the autocorrelation function. And because we calculate now the difference of the two, which gives us the slope here on the left-hand side, we will end up after maybe more iterations here. This is a little bit idealistic because we end up in the next iteration already at the top. But if you see now, if we arrive at the top, early minus late produces 0. Yeah, so the loop is like converging with the two correlations up from the left side, up the correlation function until the peak. And then when it reaches the peak with the two probing calculations of autocorrelation or cross correlation here, it stops moving because this difference of the two correlation values is approximately 0, and it does not move further, so it keeps this time delay. If now the time delay changes over time, this loop can also follow this, because then the peak is moving again in autocorrelation to the right or to left, and the loop is following this. If we would start from the right hand side from the autocorrelation function, we can also see that we would diverge also to the peak. Another thing what we already can see, if we are too far off with this gradient ascent method, for example, if we start far away from the peak on the left-hand side, we will not reach the peak because the loop will not move. Everything's 0. So, and this happens also from the right-hand side. What does this tell us? It tells us that we have to initialize the loop already on the peak here of the autocorrelation function, so close to the global optimum of the autocorrelation function. Otherwise, we will not end up at this peak. But this is a natural. This is natural for all gradient methods. They only can converge to the global optimum if we initialize close to the global optimum, or if the complete function is convex or concave, depending on whether you're minimizing or minimizing or maximizing over this function. In our case, it's concave here. So because we're maximizing, and we're maximizing over a concave function, so trying to find the peak of this function. If this function stretches over the complete area that we're looking to, then all the gradient methods, no matter where we initialize, they will converge. However, usually, and we will see in the next lectures, how we can initialize. In general, we have to initialize our problem close to the peak or the global optimum of these functions in order to use gradient ascent methods. So thank you very much for this first session. I think we could discuss some questions now, if you have.
Okay, thank you very much, Felix. And we have no questions so far.
Okay.
So I invite you to take a 15-minute break, and we will return at 10:15. Okay.
Okay, good.
Okay. So see you in few minutes.
See you in a few minutes. Bye bye.
Bye. So returning from the break, Dr. Felix, we have one question from Carlo Ferigato. The question is, what are the real-time constraints for the estimation of the time delay? The audio, you just need to
I need to switch it
open
on.
your microphone. Okay, thank you.
The real-time constraints. So you have to produce a new time delay estimate for each period. So this means that you have to produce each millisecond. This is the shortest period today available for the sequences. So the shortest period for all the signals. They're planning shorter ones now, but it's approximately 1 millisecond. So each millisecond you have to produce a new. In the extreme case, every millisecond you have to produce a new time delay estimate. So your hardware needs to produce for each satellite, calculate 3 correlations, as we have seen. So early, late correlation, every millisecond. And then maybe for, if you are considering only one frequency, one system, 12 up to 12 satellites, so 12 times 2 correlations you have to perform per millisecond. And then you have seen from the update scheme, it's very simple to update the feedback. It's just a sum of the previous estimate plus this difference of the 2 correlations. So you have to perform also the difference of the 2 correlations. If you then multiply this with frequencies and systems, this is getting a little bit larger. And the problem is that the correlation the correlation is quite long. So the sequence is 1 millisecond long. So you have 2,000. If you, for example, if we take the GPS-CA code case, many people are familiar with this. So if you consider a bandwidth of 2 megahertz, two-sided, so you have a sampling rate of around 2 megahertz, then you have around 2,046 samples per millisecond, and then you have to perform this correlation, which is a complex. Usually a complex multiplication of 2,046 values. And so this is this drives the complexity of the receivers, how many correlations you have to perform. And this is also, if you look at receiver architectures, you have the implementation of correlators is a huge deal, and this drives the complexity. To close the loop is very simple, as you have seen after that, and you can separate this usually. So you have hardware blocks that are performing only correlations all the time, and then you have maybe a DSP or something that is closing this loop and feeding back to the hardware the new value for the next correlations. Okay.
Okay, thank you, Felix, for your answer. We don't have more questions, so if you want, when you want, you can share your screen again and continue the presentation. And after the presentation, we will have a final Q&A session.
Yeah. So please write your comments during my talk. You can continue writing your questions and comments into the chat, and we will try to answer them all in the end. We should have enough time, I think. Okay, so I will share my screen. Yes. So this is the second part of the training today. So first part, we have understood basically and mathematically what is the multiple access, what are different multiple access schemes. We have seen how the signals of the different satellites are separated and how this process of separation is done with correlation of the known of this using the sequence of each of the satellites. If we talk about a direct sequence CDMA approach, how to separate them by correlation, by correlating the signal with the sequence of each of the satellites. And then we have also seen fastly how we can then estimate the time domain using correlation also, because we don't know the time delay. Correlation maximizes with the true time delay of each satellite. So we have seen a method, a maximum likelihood estimator, and then a feedback structure, a simplified feedback structure that provides us with estimates over time of the time delay. And this is also converging to a good estimate of the true time delay in general, if we initialize this process well enough. And we discuss about this initialization of this process tomorrow in the signal acquisition part, and the parameter tracking part will come back to this gradient ascent method that we just discussed on the time delay estimation. What we also have seen is that the autocorrelation function plays a role in this gradient ascent method, because we're calculating, as we have seen, the function is symmetric as all the autocorrelation function, the autocorrelation function is, and in practice it's a cross correlation function. Because our model in the receiver might not fit perfectly to the transmitted signal model or the transmitted signal, because each satellite has a different characteristic. The model in the SysICD, so the signal in space interface control document, is also a little bit simplified. However, the model is sufficient because all the receivers, they work nicely. We have just to take care of the domain of biases, and I guess in the PPP part, precise point positioning part, in this training later, you will also hear about receiver biases and maybe satellite biases. But in general, it's one bias, it's a receiver bias. And we have like a disturbance of the time delay estimate is disturbed, is not only the error has not a variance, but it can have a bias because of the model mismatch, because the correlation does not match perfectly the model of the receiver that the receiver uses for the signal does not match perfectly to the received model. And this can cause biases in the correlation, in the time delay estimate. And these biases, they can be up to meters in the range estimate. So they lead up to meter errors in the range estimate, because you don't know exactly the shape of the signal as it arrives from the signal. Again, there is a lot of effort put into these biases. So there are systems these biases with respect to certain receivers. There's also, as I mentioned in the first part of this training today, you can use high gain antennas, so to lift the signal up above the noise floor and then try to derive an analysis of the signal. And with this, you can calculate the mismatch, or you can calculate the true transfer function of the satellite. So how does the satellite really transmit the signal? And based on this, you can then mitigate these biases, signal biases in the receiver also. There's certain ways of doing this. It's very important if we want to get to centimeter level accuracy. These biases are very important in the end, and the model in the correlator that the signal or the receiver is using is very important, or we need to apply a correction afterwards. If we know the bias, we can use the mismatch so that we can use this and correct the bias later. We have seen that the autocorrelation function is very dependent on the chip pulse shape, or is only dependent on the chip pulse shape if the pseudo-random sequence can be assumed random. And for most of the case, it is a good assumption. So the pseudo-randomness is kind of random, and we will then and we see that then the autocorrelation function is only dependent on the chip pulse shape, and the gradient method that we just looked into is dependent on the autocorrelation function of the signal, or cross correlation between the model and the received signal. And that's why we will now have a look into these chip pulse shapes. So how do they look like? We also have seen that they cause they different chip pulse shapes can separate the signals also in the band, and we want to understand how this works, because we have seen in the beginning this spectrum where we had the different signals separated in the same band, different GPS and Galileo signals, and we want to understand today or now how this works with different chip pulse shapes. And then we also will have a look into how does the satellite multiplex different signals onto its carrier frequencies, and this is what's called multiplexing. And I'm also explaining this because this is also part of the GIC-ICD, so the Signal in Space Interface Control document. If you read this from Galileo, from GPS, they will talk about the multiplexing in more or less detail. So they have maybe a more detailed description. So Galileo has a quite detailed description how they multiplex the signals. Some others, they do not explain this in bigger detail. But it's important. You need to know after down conversion and so on how to separate the different satellite. Not only you can separate them all by correlation, but some of them, it's also important to understand what's the multiplexing scheme to implement the signal processing. And that's why we also have a look into these methods, and I will explain how this works. So let's start with the chip pulse shapes first. So we will look into the rectangular chip pulse shape. Then there's the binary offset carrier signals, box signals. This is widely used in GNSS. It's kind of the second generation of chip pulse shapes, because they started all with rectangular chips. So GPS and GLONASS, they started with rectangular chips. Very traditional implementation of these spreading sequences. If you open books from the early days when spread CDMA systems were introduced, everything's always rectangular, the chip pulse shapes, but they don't have to be. Later, people looked into designs that the chip pulse shapes are not rectangular. For example, in the IS-95 standard or the CDMA 2000 standard, we have a sync pulse with a different chip pulse shape that minimizes the multiple axis interference, so the intra-system multiple axis interference, because that's more dominant for communications, because you have more users. We have only 10, 12 satellites that interfere each other. In communications, you have hundreds of users that use the same band, so the multiple axis interference is a more driving factor. This is also, we can see this also in the design of GNSS. Nowadays, the signal design in the past was it was a noise limited system. We had only GPS, and then if you look at the history, you had GPS and GLONASS starting more or less at the same time, and they were separated in bands. If you remember the first day, if you look at the frequency plan there in the material that we provided, you see that GLONASS and GPS were frequencies. They had no interoperability planned in the beginning, so they were separated. So they were noise limited, mainly because we have only a few users that use the channel, only the satellites. I mean, the users don't transmit anything back to the satellite, so it's only the satellites broadcasting. You have maybe 10 sources at the same 10, 12 sources at the same time. That you can receive or that are transmitting in the band. So this is not a huge number. So the design was more focused on the performance when you have only noise. Today, the performance of the signals are more designed to, and this was introduced by these box signals, to also mitigate interference among the different systems, because they have realized that they're moving slowly from a noise limited system to an interference limited system, because more and more systems are coming into the same bands transmitting. They're all introducing new services. They are thinking about in the evolution of transmitting more signals. Some are thinking about transmitting signals only designed for the acquisition process, which we will discuss tomorrow, that starts the delay estimation, and then for the tracking to be very precise and very robust, use another signal. Then there came up the idea of designing pilot, to introducing pilot and data signals, so that on the data signal you have the satellite data, on the pilot signal you have the freedom to track however you want the signal without taking care of the navigation bits. So you can integrate longer, you can make longer correlations, you can increase with this the processing gain. You can increase the processing gain with this. And so there's a lot of movement still going on in this evolution. But we will start here. So with the classic one, the rectangular one, then it's already second generation chip pulse shapes, the binary offset carrier signals, very popular. And then there was already some generalizations of the box. So we have composite box, which is a sum of different box signals as a chip pulse shape, and time multiplex box. So this means that we have inside a chip's a spreading sequence, not all the symbols are the same. We could have different symbols, right? So we can have like 20% rectangular, 20% box signals, and so on. So this is what's time multiplex box is. And we see, as an example, we will discuss the implementation of the Galileo Open Service, which is a composite box signal, and we will discuss the L1C signal of GPS very briefly, which is a time multiplex box signal. And then we will dive into the multiplexing part. So signal mapping, multiplexing methods. I will explain shortly what are the objectives of these methods, why do we need the methods on the satellite. It's mainly to modulate the signals with most efficiently, so with no power loss. So to have all the power really, so have minimum losses of power on the satellite, because we need all this power to transmit the signal. You have to understand, I mean, the signals you need on the satellite for one signal around 30 to 40 watts to amplify the signal. And on the satellite, the power is limited, right? So we have only a certain size of solar panels that can only generate a certain power, and solar panels, if you make them larger, satellites get higher, have a higher weight. If they're getting heavier, it's more difficult and more costly to launch satellites. So this drives up the costs dramatically, and also the size of the satellite, the size of the amplifiers, the power consumption of the amplifiers, and so on. So it's good to be power efficient always, to use as much as possible the power that you receive on ground in your receiver. Don't follow these discussions where people tell you, hey, I'm just losing half a dB or 1 dB. Oh, this is a lot of power that you lose. 3 dB is half of the power is gone. So you should, as efficient as possible, design your front end. You should have as much gain as possible with your antenna. You should make sure that you don't lose anything in your receiver, because there's a lot of effort on the system side to be as efficient as possible, to provide as much as power as possible to the user. So there's a lot. You take care of this. I mean, okay, you cannot always try this. You cannot always achieve the optimum receive power because of maybe complexity constraints or constraints in your device or anything. But have a look on these losses in your receiver and so on, so that they are not growing too large. And then we will go into these signal methods and interplexing or multiplexing methods, and we'll have a look into the simple interplex method and the outbox method. For sure, I will just mention that there's also time multiplexing of the signals, and it's also applied on some systems, but we will not look into this in detail. Okay, let's start with the rectangular chips. So we can write this mathematically as P rectangle, 1 over square root of TS, and then UT minus TC half minus UT of minus TC half. And UT here is the Heaviside step function. Maybe you have seen this already in your engineering signal processing or mathematics course. It's a function where you have the function is 0 up to t equals 0, and then it's 1 from t equals 0 until infinity. Again, this writing of the chip pulse shape is that the energy of the chip pulse shape is 1, or the power of the signal is 1. The rectangular chip pulse shape, as I mentioned already, is considered as the classical chip shape. So we have in all the original spread spectrum signal systems, they use rectangular chips. We get in the end, based on this chip shape, we get a binary phase shift keying signal. And how does this look like? In time domain, we have this chip shape here. So P rectangle of T times square root over TC. Then we end up at zeros and ones here only in the chip pulse shape. Yes. So this is one symbol of the code. Is then represented by this symbol. And we end, as we see on the right-hand side, we see the real part and the imaginary part of our received signal. So we end up in a BPSK modulation between the levels, the square root of the power and the negative of this. Yeah, the Fourier transform of this chip pulse shape can be also easily calculated. If you can use the integration, just the synthesis, just the Fourier straightforward solving the Fourier integral in a stepwise manner. So. So integrating over the different parts of the chip pulse shape as a sum, and then you end up easily with this here, this result. This is the sinc function. The sinc function here in this course is defined as sinc of t equivalent to sinus of pi of t divided by pi of t. That's the definition also used by MATLAB. And then based on our previous discussion, we can easily write now the autocorrelation function using this Fourier transform. This is much easier than simulating the sequence and then calculating the autocorrelation. But you can make this exercise in one of the numerical programs, Python, MATLAB, C, or whatever you use. Calculate this autocorrelation function either based on the spectral representation of the chip pulse shape, or derive a sequence, for example, of GPS, modulate that with the chip pulse shape, or convolve this with the chip pulse shape, and then calculate the autocorrelation function. And you will see that the model that we introduced here is not very bad. So they're very close. The link is the resemblance is large. So we can calculate this now here using Wiener-Khinchin theorem. either in the spectral domain using the spectrum, or in time domain using the time representation of the chip-by-chip. How does this look like? For infinite bandwidth signal, we have on the left-hand side the autocorrelation function of the rectangular chip shape. So this is a triangle starting from minus TC to 1 TC in its length. And there we already see with our gradient method, we have to start inside this triangle, right? So our accuracy from this initial estimation process that we will discuss tomorrow, signal acquisition, has to end up with an accuracy of 2 TC, right? So from minus TC to 1 TC, we have to, the error can be maximum 1 TC from the true value. So we have to end up inside there with a first guess, and then we can start our tracking with the delay lock loop and end up at the peak, tracking and then following the time delay. On the right-hand side, we see the power spectral density, which is following this square root, absolute valued square of a sinc function, and we have this rapid decay of the power towards higher frequencies. Yeah, binary offset carrier signal. So here we can see these chip pulse, the rectangular chip pulse shape. The power of them if we look at the frequency of the spectrum, is concentrated around 0, so around the carrier. So box signals are now signals that will shift away these main lobes of the spectrum from the carrier. So we can define these signals now. Box signals became the standard of GNSS signal design. Besides using rectangular chip shapes, their chip pulse shapes are formed by the product of a rectangular pulse. This is the same formulation as before, just with some different variables. So TC is changed into NCFR here, and a sine or cosine square wave subcarrier. So we have now a subcarrier. So the chip rate is NC. So this is the multiplication. The box signal is the multiplication of these two. So the rectangular pulse and a subcarrier. And we have now the chip rate, which is NC, and then the chip duration is 1 over NCFR. FR is a reference frequency. That is in GNSS, they always use 1.023 megahertz as the reference frequency. And then we have also the subcarrier rate NS multiplied with FR, then is the subcarrier frequency. And then let's say the terminology or how they use this, they say BOC NS NC, so box signal with sine subcarrier. So this is the first option of the subcarrier multiplication with the sine of a sinus, of a minus sinus, and the other formulation, BOC cos NS NC, is then a signal with a cosine subcarrier. And we'll see it has a significant difference using one or the other subcarrier. Yeah, so here's the multiplication of the two. So the rectangular chip shape P and NC of T, and the subcarrier G of NS of T. And this is just, it's time limited, the pulse. So outside the chip duration, it is 0 because of the formulation of P of NC of T. So BOC11, just to mention this was already in the literature under a different name. It was called biphase Manchester pulse. It had the advantage that in early days of telephone communications, you did not have power at the carrier, and so you could cut out the carrier power at the receiver, so you could get rid of a lot of noise on the receiver side. We also get a BPSK signal. Box signals achieve the FD-CDMA, and we will see this right now. And then we can also define N as equal to 2 over NS divided by NC. The number of half periods of the subcarrier within the duration of one chip. This is just this is used also in the literature a lot. the higher n, the higher the gabor bandwidth of the signal becomes. The gabor bandwidth of the signal can be given like the concentration of the signal around the center. So the higher the gabor bandwidth, the less concentrated the signal power is around the center. And in our case, then the gabor bandwidth is also related to the formulation. We have not discussed this of the Kramerau lower bound of the time delay estimation, which means the higher the gabor bandwidth, the lower this lower bound. So this means the higher the gabor bandwidth. So the more power we push to the edge of the frequency band, the better we can estimate the time delay. So the higher the accuracy of the time delay estimate becomes for this signal. So the signal shape also influences the time delay estimation quality or accuracy. So here we see now on the left-hand side, we have the sinus block for a BOC11 signal, and on the right-hand side we have the cosine. On the right-hand side we have the BOC cosine 11 in red. And here we have the autocorrelation function of the two. This kappa equals 1.5 means that the highest side level or side lobe level is 1.5, is 50%. This is important when it comes back to our gradient method, because we have to end up, in order that our gradient method will converge here to the global peak that is in the middle at 0, we have to start and initialize this gradient method on this peak. So in the middle of the autocorrelation function. If we start too much to the left or too much to the right, we end up maybe on the side peaks of this function with our gradient method, and this can we can then have serious errors in our time delay estimation. So we can see here that the autocorrelation function contributes directly to the robustness of this time delay estimation feedback system. Another thing that we can have a look here is that the peak of the two autocorrelation functions is different. The sharpness, so the red curve is sharper at the peak than the black curve, and this sharpness of the peak also contributes directly to the accuracy of the time delay estimate. The sharper the peak, the better you can estimate the time delay with higher accuracy. And we will see, the sharper the peak, the more power of the signal is pushed to the edge of the band. And we see this immediately on the next slide, and more dominantly on when we go to higher BOC or to higher subcarrier frequencies. But here we already can see this. These are the two power spectral densities of the cosine BOC in red, and the cosine BOC in red, yes, and the sinus BOC, the BOC sinus in black. And you can see there's more power shifted to higher frequencies for the BOC cosine. So the peak of this autocorrelation function gets sharper. So we can, in principle, synchronize with higher accuracy. However, you have seen the side lobes of the autocorrelation function grow, so the robustness of the time delay estimation processes may be jeopardized here a little bit. And we can see this more clearly when we now move to BOC21. So we have two cycles of the subcarrier within one chip shape. On the left-hand side, we have again the BOC sinus. On the right-hand side, the BOC cosinus in red. If we now move on to the autocorrelation function of the two, we can see that the peaks are now growing dramatically with higher subcarrier frequency. So now it's twice the chipping frequency. And then this kappa value, which is here the highest side lobe of the autocorrelation function, is now 70%. So depending on what kind of synchronization algorithm you you use, you can so your loop can end up converging to one of the side peaks. And this also increases the demand of the initialization process, because you have to initialize on the peak of this, or you have to define other methods for initialization, maybe tracking also the subcarrier or something like this. This is what's done in the literature, or proposed in literature also. Yeah, now we get this more clearly. The properties of Bock sinus and Bock cosinus here with the spectrum of the Bock 2-1 for both of them. We can see more power is pushed to the higher frequencies for the Bock cosine, and we can also see that less power is distributed among close to the carrier, which is here at 0. While the sinus has still some significant power around the carrier, but has much less power for higher frequencies. So this gives you already some kind of degree of freedom to design and to the signals, and to shift the main part of the power of the signals inside the spectrum to achieve separation with other systems and other services. More pronounced, we can also look now at a Bock 4-1. So sinus and cosinus Bock again on left and right for a Bock 4-1 signal. And then let's look at the autocorrelation. This already gets quite terrible here already. The kappa is already nearly 90%, so it's difficult to separate the peaks from the global peak. Now the peak gets sharper and sharper, we see that. So this is good for the accuracy, but the robustness of the estimator is, so the complexity is getting higher, maybe, to really with confidence get to achieve the estimate of the peak here. And here we see it now very clearly in the spectrum. So we see that the cosine Bock has much less power around the center, more power for higher frequencies, and the sinus Bock has more power around the center and less power for higher frequencies. And this is what is used. For example, if you think back, or if you look back to the picture from the last lecture that we had for the Galileo PRS service. The PRS service is a cosine Bock because it's shifted very far away from the carrier and has then more power for higher frequencies, and no power, at least, or very low power around the carrier. And this helps now to separate from signals that are focused on the carrier, where the power is focused on the carrier. So here the Bock signals helped to introduce the frequency division, code division multiple access in GNSS, and to reduce dramatically intra and inter-system multiple access interference. Yeah, what is composite Bock? Composite Bock is a summation of two Bock signals. So the C-Bock, composite Bock signals are composite of a linear combination of several Bock signals. So a C-Bock signal with two Bock signals can be given as P C-Bock of t, and then we have here two coefficients. So psi is a normalization coefficient, and omega is a weighting coefficient between the two Bock signals. So we have P of Bock A, AB, and P Bock CD, so two Bock signals, and they can be combined with plus or minus, and then there's a weighting. Omega is a weighting between the two. Yeah, and the weighting is omega is from 0 to 1, and the Fourier transform of this signal then also can be given as P of C Bock of F, and equals this normalization coefficient psi, the square root of this, and then we have the weighting between the two Fourier transforms. The PSD, so the power spectral density, as the normalization coefficient, will make sure that the Fourier transform, the integral of the square root of the Fourier transform, has the value 1. So then this is equivalent to the power spectral density, this absolute value square of the Fourier transform. And then we have this psi multiplied here with the 3 terms. So we have the power spectral density of the first box signal with the weighting coefficient plus minus 1 minus the weighting coefficient omega times the power spectral density of the second box signal. And then we have some kind of a cross power spectral density of the 2 signals, and depending on whether we use the plus or minus sign of the 2, we have here also the plus minus the cross power spectral density of this 2 signals. The other correlation function given equivalently by this, and now we have here the definition of this psi factor. It's just normalizing the signal power to 1 or the autocorrelation function to maximum 1. It's just this form. We can just introduce this formulation either in frequency domain or in time domain. And with this normalization coefficient, the Bock power spectral density is equal to 1. Or the power of the signal is 1, and we can write this here in time or frequency domain. Yeah, for the Galileo open service, there's 2 signals combined in a composite Bock. This is called Bock plus, which is the data signal of the open service of Galileo, and then we have also the pilot signal, the Bock minus signal, and the following 2 CBOC signals are composed. So we have then the Bock plus, which is the data component, is a square root of 10 over 11 Bock 1 plus a square root of 1 over 111, so 1 over 11 Bock 6 1. So 1/11 of the pulse is square root 1/11 is a 6 1, so very small part is 6 1 and the bigger part is 1 1. And we use a plus here, so it's the addition of the 2. We can also use for the Bock minus, which is the pilot signal, we use the difference of the 2. So we have a Bock 1 1 minus a Bock 6 1. We will see this cancels out the cross power spectral density of the 2. Because we used in one the plus and the other the minus. That's the reason why this was done. The overall PSD of the sum of both signals with 50% power for the data and 50% power for the pilot signal. So we end up just with, if we have half of the powers given to the Bock plus and half of the power given to the Bock minus, we end up exactly at the overall signal has 10/11 of the power of the power spectral density of Bock 1 1 and 1/11 of the power spectral density of Bock 6 1. How does this look like? So the chip pulse shape on the left hand side is the Bock plus signal, and on the right hand side we have the Bock minus signal, and we can see that the 2 are different because of the one uses the plus and one uses the minus. If we look now at the autocorrelation, the power spectral density is interesting. So the Bock minus has more power shifted to higher frequencies. For the main lobes, they more or less lie over each other, but for higher frequencies, they have a significant difference in the pattern here. And here's the autocorrelation function of the 2. So we have the Bock plus is a little bit less sharp than the Bock minus. This makes sense because we want, with the data signal, we just want to receive the data. So we need some kind of a autocorrelation function with a good peak to synchronize on and to robustly synchronize on. And this is quite good because here we see that the next side lobe of the autocorrelation function is less than 50% of the signal. And the Bock minus, the pilot signal, has a bit sharper peak, so offers a little bit better synchronization accuracy. And we have also the side lobe level is a little bit lower, so this is designed towards the right direction. Um, the the time multiplex block, but maybe I can answer. I've seen here is one of the questions is there any formal definition for the robustness of the estimator? This is a difficult question, but it's mainly how high are the side lobes of this autocorrelation function here. So if you want to find the peak, you will as we will see later, we will also look in a we had only the real case so far considered, but if we also have an unknown phase and an unknown Doppler frequency, we will end up maximizing the absolute valued square of the cross correlation function, and then these peaks. And then we try to find a peak, of this function. And this function, if this has high side lobes, then we need to implement a more complex method to find this highest peak, right? This cannot be a gradient method anymore because we have several side peaks. We could end up initializing on the side peak, and then the gradient method just iterates up to the peak of this side lobe, and that's it. It will stay there. The gradient method does not have the capability then to jump to the main peak. There are some methods that jump then also if it converges and jumps and so on. So you have to think about methods how to robustly find the global optimum of this function of the autocorrelation function, as we have seen, which is the cost function of our maximum likelihood estimator, and this is a definition of robustness in the end. So the height of the side lobes of the cost function of the maximum likelihood estimator. Yeah, so this was composite BOC, time multiplex BOC for it's called TM-BOC. For TM-BOC, different chip pulse shapes are used for different chips of the PR sequence, and time multiplexed BOC chip shapes with two different BOC chip pulse shapes, which are emitted each TC seconds, can be given as. So we have then a probability P for the BOC chip shape AB, BOC AB, and the probability 1 minus P for the chip shape BOC CD. So with a certain probability, we get different shapes. In the case the signal source is negative, equally probable, so which means that the positive and negative symbols are equally probable, NEP, the PSD of a time BOC signal can be given as just the sum of P times the power spectral density of the BOC AB plus 1 minus P, the power spectral density of the BOC CD. And this gives us the overall power spectral density of the TM BOC signal. And the autocorrelation function as well. So we have just the weighting with the probability and summing the two different autocorrelation functions of the two chip pulse shapes. In the sequel of GPS system modernization, the L1C was defined as the future open service. So this is the future open service of GPS. I think there's 2 or 3 satellites already transmitting, maybe 4, already transmitting the L1C signal. And we have also 2 components. We have pilot and data, as for the Galileo signal. And here the pilot and the data, so we have first for the pilot the 29/33 BOC11 and 44/33 for BOC61. And for the data we only have BOC11. If we now combine this with a 75 to 25% share between pilot and data, we get to the exact same power spectral density in the end as the composite BOC in Galileo. It's That's very nice. So they have the same power spectral density, but they have a complete different realization. And you can also see that the GPS, they have much more weight on the pilot signal. So 25% more power on the pilot than Galileo. Galileo has 50 on the pilot and 50 on the data. GPS has only 25% of the power on the data signal. And has, instead of having a composite BOC, a TM BOC implementation. So, but these are just two examples. I mean, you can play with this composite BOC. You can have an infinite sum of BOC signals, and you can also not only have two different signals in the in the sequence, or two different chip shapes in the sequence. You could have all 3, 4 different pulse shapes repeating with different probabilities. So these concepts can be generalized also to more chip shapes, more BOC, more composite signals, or more time multiplex signals. Yeah, these are the main these are the main chip shapes used today in the signals. There's only the Beidou signal. They have a different variant of the composite BOC signal, but most of the signals that you will encounter in the GPS world have either BOC, rectangular, composite BOC, or time multiplex BOC signals nowadays. And that's why we stop here. I mean, there's a lot of research done at the moment, and already in the past, that the people looked into designing chip pulse shapes in a different way, looking into band limited chip pulse shapes, because most of these rectangular BOC signals, they have infinite bandwidth if you generate them with infinite. Yeah, with infinite, they have infinite bandwidth, and maybe on the satellite, I mean, in reality, you don't have infinite bandwidth. So people also looked again into generating signals with an infinite bandwidth. Then we cannot have like sharp edges in the signal. We cannot have purely binary signals. We will have transitions between the states that are not where we have non-binary values of the signals. But in reality, anyway, the signals that are generated, they will never have an infinite bandwidth. So also these rectangle binary offset carrier signals, they're not as exactly binary when the satellite generates them. So that's why there's a lot of research. People also look at different multi-carrier signals, OFDM signals for ranging. So there's a lot of things looked into, and I think there will be, in the next evolution of the signals, some of these techniques will be implemented. So there might be a move away from strictly binary signals to non-binary signals in the future, as bandwidth will also become more and more an issue, and also efficiency on the satellite will become more an issue. Also, the inter-system and intra-system interference, as I already mentioned, these are both growing. Because the satellite systems, they're not only ramping up all the power, so the evolution of GPS, Galileo, Beidou, all the satellites, they have more power, so they are investing more in weight of the satellite. This is one thing. The other thing, they're getting more power efficient, so there is more power available on the signal side. This increases the intra-system interference in general, and also increases the inter-system interference. So we're moving towards an interference limited system, starting way back at the beginning of GPS and GLONASS, when they had a noise limited signal. So these interference issues become more a design driver. And we can also see this in the multiplexing. So what is multiplexing methods? What is this about, and why do we need that? So the goal of multiplexing or mapping several signals SN onto one carrier, because the satellite, they have only a limited number of amplifiers, and they're trying to have only one amplifier per carrier frequency. And in order to map then several services, so for example, one data signal and a pilot signal and maybe another military signal on one carrier, you have already 3 signals that you want to map on one carrier. How to do this efficiently on the satellite, because we don't want to lose a lot of power towards the transmission of the signal, and then on the user side on the ground. So what we want to achieve is minimal crosstalk between the signals in the generation, and maximal power and bandwidth efficiency. So we want to not waste any power at best, and we want to have using the bandwidth efficiency that we have available. Each signal provides a different service in this formulation. So pilot, data, open service maybe, and then maybe a military signal, and all the 3 have to be interplexed. In general, there are 2 main strategies. So one is time multiplexing. So we could time multiplex the signals, and when we then correlate over time, we can still receive all the time multiplexed signals. And also what we can do is frequency of phase multiplexing, and this is what we are going to look into. Yeah, constant envelope is something that you will read a lot in the literature, and this is generally a topic always for satellite services, because you want to be very efficient in time, in power. So power efficiency you want to have high. So what you want to achieve is that the peak to average power ratio of the signal is close to 1, which means that the maximum of the absolute valued square of the signal divided by the expectation of the absolute valued square value of the signal is 1. What does this mean? This means that we can preserve a constant envelope of the signal. Is very beneficial for the amplification of the signal by the high power amplifier, which in the end, before the antenna has to amplify the signal on board the satellite. And if we have a peak to average power ratio that is 1, which means that the signal has a constant envelope, means that we can drive this amplifier in saturation, so close to its maximum value all the time, because the signal has a constant envelope. And with this, we can then prevent out-of-band emissions and power inefficiencies if the signal has a peak to average power ratio of 1. So is a constant envelope, and we can drive the amplifier close to saturation, which means we can drive the amplifier in its most effective configuration. So not losing the power losses then minimum due to the amplifier on board the satellite. And we get most power amplification to our signal. So the goal of these interplexing methods is to achieve a constant envelope of the signal. So first, we can have a look at what's called interplex, a phase modulated radio frequency passband signal in a phase shift keyed phase modulated, so PSK PM system, can be given as S tilde of t equals the square root of twice the power of the signals times sinus of 2 pi carrier frequency times the time, plus a phase term phi of t here. And the n-channel interplex phase modulation, this phase term here, is then given by a superposition of the different signals. And we have here beta plus the sum of n from 2 to capital N of beta and Sn of t, so 2 to n, the signals 2 to capital N are summed up with these modulation coefficients beta, and then we multiply everything with the first signal, and we also have added the first modulation coefficient to this. So P is the total power of the signals, FC is the carrier frequency here, N the number of channels or the number of signals that we multiplex on one carrier, and beta n are the so-called modulation angles. And we have binary signals. So this is a method how to interplex onto the carrier of a passband signal. This is phase modulation, phase shift keying, several of these binary GNSS services or signals that belong to services. Yeah. How does this work for two signals? Let's have a look. How does it work for two? So we can apply the formula defined on the previous slide as tilde of t, and then we have two signals. So we arrive at this formula where we have the carrier frequency 2 pi fct plus modulation angle 1 times s1 plus modulation angle 2 times multiplication of s1, s2. So two signals. We can now use these trigonometric formulas, especially the third one. So the first two are standard, you can find everywhere. The third and the fourth one need some explanation. If S of n is a binary signal, this is only 1 or minus 1, right? Then the cosine of beta Sn is equivalent to the cosine of beta n. And if you go to the sinus, so sinus of beta n, Sn of t, is then the equivalent of Sn times sinus of beta n. We need that for the formulation. So if we now apply these trigonometric formulas to the formula or to the equation on the top of the slide, we end up with this formulation here. So we have square root of 2p times sinus of 2 pi fct, and then we have cosinus beta 1 cosinus beta 2 minus s2 of t times sinus of beta 1 sinus of beta 2. And then on the other hand, plus, we have a plus here, the cosine twice the power square root of it times the cosine of 2 pi fct times s1 multiplied with sinus beta 1 cosinus beta 2 sinus 1 sinus 2 s1 s2 times cosinus beta and beta 2. So what we can see here, we have on the sinus carrier, on the in-phase carrier, we have the cosinus beta 1, cosinus beta 2, S2 cosinus beta 1, sinus beta 2, two signals, and we have also two signals on the quadrature of the carrier, so the cosinus part. Now we can choose the two. We can first calculate the power of all these four signals. So we have two signals on the sinus carrier part and two signals on the cosinus, so the quadrature of the carrier part. We can call this the carrier power, which is the first signal on the sinus part, or the in-phase, the quadrature part, sorry, the quadrature part is the sinus part and the cosinus part is the in-phase part. So we have the carrier power here with p cosine square pi beta 1 cosine square beta 2, the signal power of the signal 1. As we go back here, this is the power of this signal of the second term in the cosinus part of the carrier of the signal with the multiplied with cosine 2 pi fct. So the in-phase part of the signal, the first term, is here P1, and then we have P2, the power of the second signal, and then we have an intermodulation signal, which is here the signal that is given by the multiplication of S1, S2 in the second term of the in-phase part of the carrier. Yeah, so PC is the carrier power, P1 is power in channel 1, P2 is power in channel 2, P intermodulation power, PIM. And if we choose now beta 1 equal pi over 2 and beta 2 pi over 4, because we can freely choose these angles, we get that the carrier power is 0 and the intermodulation power is 0, and we have half the power in channel 1 and half the power in channel 2. How does this look like if we... So this is what's called the quadrature binary phase shift keying modulation then.
and we see that we have one channel operating on the on the in phase, on the imaginary part of the signal, and the other one in the real part. So this is the equivalent baseband signals S of t with the passband signal given by S tilde of t, and this is square root of 2 times the real part of st e to the power j pi 2 pi fct. So that's the passband signal. The complex baseband signal, we can see that the signal constellation here, which is the representation of real in the real and imaginary part of the signal, we can see that all these points, they lie on the unit circle or on a circle, and if they all lie on a circle, the phase states of the signal, or the possible states of the signal, because the signals are binary, then we can talk about a constant envelope signal, because they are lying on this circle, which gives us the constant envelope of the signal. So we have all the 4 possible states here on this circle. So we have this interplex system generates, or this interplex generates a constant envelope for 2 signals. We can now expand this because the phase transitions that can happen, some of the transitions, they go through the 0. And if we have a higher sampling rate, and if the chip pulse shapes are not exactly binary anymore, then we also have values of the signal that are transitioning through the 0 here. And this, if we calculate the peak to average power ratio, it diminishes or will decrease our peak to average power ratio. Will increase our peak to average power ratio. What we need to do is we have to move the signals back closer to the circle, and we can achieve that with phase transitions to be mitigated by an offset QPSK method, where we offset, as given here in the formula, the one signal by a certain time offset to the other one. If we use the same chip pulse shapes for both of the components, then this is exactly half a chip offset that we have to introduce. If we use different chip pulse shapes on the 2 carriers, then this can be having a different delay, but there is a delay that will help to reduce these phase transitions, and this is what's called staggering of components. There's also methods available for staggering not only 2 signals, but many signals that are multiplexed on one carrier. And there's a paper of one of my students about this, or one of my colleagues about this, from DLR. If you're interested, you can find this on the IEEE base. We have looked into staggering 3, 4, 5 signals and finding the optimum time delays for the staggering, reducing the peak to average power ratio as much as possible by getting rid of the transitions that go through 0. This is pretty much what it does. But in principle, for 2 components, this is what's called offset QPSK, and you can also find this for communication systems, very common, in order to efficiently transmit signals. Also for communication systems, in the past this was more important. Today this is getting important again when we talk about Internet of Things, low power devices distributed among an area. These devices do not have any power at all, or they can only get the power over like an RFID scheme, or they have very limited power, so they also rely on efficient transmission schemes, and they come back to these concepts where you have to have constant envelope modulation before transmitting this. So offset QPSK is again in the discussion, and staggering of modulation is becoming important again. So let's move on to the case of 3 channels. So this is the formulation for 3 channels using the interplex. And I'm going through the derivation a little bit faster, but this is just applying the trigonometric formulas. It's a little bit tedious to calculate this. So applying trigonometrics, we have here then again the quadrature part of the carrier and the in-phase part of the carrier. And we can call this A1 and A2. A1 can be seen, we have 4 signals in A1 and we have 4 signals in A2. And what are we looking for in all these signals? So this is a part of the signal. For example, the first term of A1 that doesn't contribute, doesn't even transmit any useful information. So we should get rid of this by choosing the angles beta 1, beta 2, beta 3, such that this part gets 0. And then we are only interested in the signals that only have S2, S3, not the multiplication of the 2 as given here in the second term of A1, and then also here only S1 if possible. So what we end up is we can choose beta equal pi over 2, then we already get rid of most of the parts, and we end up with 4 signals. We have P1, P2, P3, so these signals that only have S1, S2, and S3, and we have unfortunately one signal with intermodulation, and this is a multiplication of S1 times S2, S3, which is a part of the A2 component here. And we end up with these 4 signals, and now we can choose beta 2 and beta 3 in order to adjust the power between the 3 signals. And here we have an example of the interplex for 3 signals. What happens is that we move from, with the intermodulation product introduces, that's why it's called here IM and then we have a lot of arrows to smaller arrows that are moving the states from a square onto this circle. And this is what's done by the intermodulation product. By introducing this intermodulation product, we achieve going from a modulation or a signal constellation diagram here in real and imaginary part of the baseband signal of the 3-channel interplex to a constant envelope signal while moving the the main states of the signals onto the circle. So this is what's done by the intermodulation product. And now we can still choose beta 2, and 3 in order to adjust the power P1, P2, P3 to the signals. And how can we do this? For example, if we want to have P1 equals twice the power of P2, and P2 should have the same power, the signal 2 should have the same power as signal 3. We can set up these equations now from these power equations that we had before. So P1 should be equivalent twice P2, and then P2 should be equivalent to P3. So we can build these 2 equations here, and we can solve the equations. Now we have 2 equations, 2 unknowns, so beta 2, beta 3. We can solve for beta 1 and beta 2. Fulfilling these requirements that the power of signal 1 is twice the power of signal 2, and signal 2 has the same power as signal 3. And then we arrive at the case that beta 2 is equivalent to beta 3, and this is equivalent to r cosine of the square root of 2 over 3. So we have 2 identical angles, modulation angles, and if we adjust the angles like this, we end up with a power share among the signals as defined here on top of the slide. So we can use one of the angles we can use to get rid of a lot of signals that do not contribute to knowledge at the receiver or do not convey any information. However, we end up with the intermodulation product that does not. It still conveys information about the signals, but the receiver, as we have learned, is just separating the signals by correlation. And so it is only correlating with some of the reference sequences of the different respective satellites and services. So it only separates the signals by this correlation in the receiver, and does usually not process the intermodulation product. It would be possible if we could process also the intermodulation product if we know, for example, the content and the sequences of all the received signals or interplex signals. However, for most of the cases, you have always a military signal among these three signals, so the intermodulation product cannot be decoded by a civil receiver, so it gets lost for our processing, in fact. And so it is kind of a waste of power, but it helps to increase the efficiency. And there's a trade-off that we have to look into. How much power on the intermodulation product are we willing to spend to get the constant envelope, to get a more efficient transmission of that high power amplifier? And in turn, is it worth doing this? Because we're investing into the intermodulation part. So we have to discuss this in an analysis. But in principle, we have this methodology to interplex 3 and even more signals. But I can tell you, if you have a lot of signals, these interplexing methods, so the power of the intermodulation product stays small. If you have a lot of signals, one signal very high power and the other signals very low power but equivalent, then this is very efficient. But if the other signals also have a larger amount of power, then you have a lot of powers you have to spend into the intermodulation product to generate the constant envelope. Because here we have in the bottom of the slide, we now have the share among the different with respect to the total power invested in the signal. So we have 4/9 of the power now for P1 and 2/9 each for signal for P2 and P3. So for signal 1, 2, and 3, and the intermodulation product also receives 1/9 of the power. So, and we could say that this is a loss in power. So it's 1/9 of the power is invested in this example to create the constant envelope, to be more power efficient with the high power amplifier. And in the overall power budget, we need to discuss this dependent on the design, whether this is worth doing it or not. Yeah, if we want to, now we find to get the final interplex or multiplexing method, we will finally discuss a method which is capable of multiplexing 4 different signals onto one carrier, and is used by the Galileo system. It's called alternative block. And in order to achieve a constant envelope, 4 signal components can be multiplexed on one carrier with. And it's getting a little bit complicated now. So we have here the baseband notation of the signal, so the complex baseband notation of S of t. And we can see here the 4 signals, S1, S2, S3, and S4. They're all multiplied with some function psi prime of m, and the others psi m of t. And then we have also S bar 1, S1 bar, S2 bar, S3 bar, S4, S bar 4 or S4 bar, S bar 4. So S1, 4, S bar 1, S bar 2, S bar 3, and S bar 4. And these are all intermodulation products. So we have to invest here into 4 intermodulation products. And to create a constant envelope. And we have to build these what are called multi-level complex subcarriers. And these are these functions psi of m, and they're given by and also this psi bar of m and psi prime of m and psi bar prime of m, and they're created by 2 functions, namely psi of t and psi bar of t. And these 4 valued subcarriers, psi of t and psi bar of t, they can be formulated by this equation here, and we can see how they are created. So these are the subcarriers created, the two fundamentals. From them we can derive the psi prime m, psi m, psi bar prime m, and psi bar m, and we can build the signal. The signal in the end has this signal constellation. So all the states, the main states, are on the constant end. They create a constant envelope, as we can see, and it's an 8 PSK. If you want to compare this to communication modulation schemes, it's an 8 PSK phase shift keying system. More important now is to understand how these different signal components end up on this Galileo signal. So if you look into the signal plan again, overview on the signal frequencies that I provided in the beginning of the course, you can see the Galileo E5 signal and also the Beidou E5 signal. They have the same spectrum, slightly different interplexing, but for the Galileo case, we have this outbook modulation. As shown here, we are looking at the power spectral density of the complete signal, and I split it up in colors into the different components of signal components. So we have 4 signal components here. So this is an E5A I signal and Q signal. So it's always data and pilot, and another signal, another 2 signals that are given by the black curve is the E5B signals in I and Q. So 2 signals, data and pilot. And then we have the 4 intermodulation products. They're IM1, I and Q, and IM2, I and Q. They have the same, and they create the power spectral density in green and in blue. The subcarrier frequency for this outbox configuration is 15 times 101.023 megahertz. And we have 4 signals then, with 1 over TC being 10 times 10 times 1.023 megachips per second. And they all use rectangular chip shapes. So the 4 signals called E5AI, E5AQ, E5BI, E5BQ, they all use rectangular chip shapes. So also the intermodulation products have rectangular chip shapes, and then there IM1I, IM1Q, IM2I, IM2Q. In fact, if you look at the spectrum of a satellite with a high gain antenna, you might not find very well pronounced these green and blue lobes, because the outgoing filter of the satellite is cutting already away this power or these intermodulation products. They're not really transmitted. However, these interplexing methods is very important to understand. They're only important up to the amplifier on the satellite, right? So we want to drive the amplifier and saturation. We need the constant envelope as the input of the amplifier. The output of the amplifier and everything that happens later is not so important anymore, because we can drive the amplifier and saturation. I mean, we lose satellite power because we maybe have an outgoing filter before the antenna, or the antenna itself acts like a filter, and then it cuts away some of the higher frequencies. And this is the case for the outbox signal of Galileo. You can find, if you look into the literature, you can find some spectra that people have measured with high gain antennas. So they can lift the signal up above the noise floor and then calculate this power spectral density. And then you can see the sum of all these power spectral densities here shown in red, black, blue and green. And you can see that the 2 lobes, the blue lobe and the green lobe, they're much smaller than you would expect now. And this is because the outgoing filter of the satellite's already filtering these lobes. So I arrived at the end of the second part of today's professional training. So we have covered signal model, multiplexing, so multiple access signal model. We have looked into how does, in a simple form, time delay estimation and time delay tracking works, which is basic for ranging. We have looked into chip pulse shapes. How do different techniques help us to separate signals in the band, how they affect the accuracy and the robustness of our time delay estimation. We discussed this a little bit, and we have seen how the satellite is interplexing different signals on one carrier. We have mainly discussed this to explain better and give you a better start when you start reading signal in space interface control documents. So SysICD, or in GPS, they have different numbers. And in order to understand this better, if you want to work or implement your own receiver in software, and then you have to read these documents, and then it's helpful to understand what's chip shape, what are code sequences, how to implement them in the receiver. As you have seen, you have to implement the signal model in the correlator. Here for the outbox, it's also important, interesting part is, and this is a very interesting and unique part of this Galileo signal design, is that you can also track all the signals together. So there is a methodology to track the complete outbox signal. So you create a complete model of the outbox signal, and then you can use, and you can see the bandwidth is really high of this signal. So you can have like around 45, 46 megahertz one-sided bandwidth. Total bandwidth two-sided is over 90 megahertz. So you can use this signal for time delay estimation. First of all, we see that we have a very huge spreading bandwidth, which means we have a great processing gain. We should have a huge accuracy, very large accuracy of the signal. This is true. We can resolve the time delay really nice. This signal is very interesting also for radar applications, reflectometry applications, where you need large bandwidth to resolve the time delay of the signal. So, but you can also track the different components separately. So you can track E5AI, E5AQ, E5BI, E5BQ, but you can also create in your receiver a model that tracks all of them jointly, and you can work with this huge bandwidth that you have available of this signal. So this makes this outbox design really interesting, because you have a lot of possibilities as a user to track the signal, either E5A only or E5B only, or outbox total, and so on. So this closes my talk today. So let's start with the last Q&A session. Now we're trying to answer the questions that came up. Thank you very much.
Okay. Thank you, Felix, for your presentation. There is a question here from Carlo. Is there any formal definition for robustness of the estimator?
Yeah. Is as I said already during the talk, it's not so easy to derive a formal definition, because it depends on what I called robustness, depends on the height of the side lobes of these autocorrelation functions of the signal. So a signal with higher autocorrelation side lobes, you need to design an estimator that takes care of this, so that you are capable of finding the global optimum, still having these side peaks. And we have discussed that most GNSS receivers today, they use gradient method. So you have to initialize already this search on the main peak, not getting into one of these side peaks, because the gradient method only can converge up to the maximum of this peak, even if it is a global optimum or a local optimum. you will then converge. If you initialize the process at the local close to the local extremum or maximum, then you will converge to this value with your gradient method. So you need to implement an estimator that searches maybe through all the delays all the time to find the global optimum. The other thing is, the higher these side lobes become of the autocorrelation function, if you have more noise, you get in the estimate can easily diverge from the peak to one of the side peaks. There's maybe a formal way of calculating this. This would be then calculating a modified Kramerau bound that considers also the side lobes, and this is what's called the Tsif-Sakai bound, and this can show you the danger of such an autocorrelation function with a lot high side lobes, because this then calculates also, depending on your noise level, the probability that you end up in one of the side peaks with even a very complex estimator that searches through all the possible delays all the time. I hope this answers a little bit the question.
Yeah, I hope so. Carlo, if you have any further questions, please send us by chat. Well, we don't have more questions, Felix. Before your final remarks for today, I would like to say that some people commented that it was difficult to connect today, and they couldn't find the email with the access link. So one tip is that you also look in the anti-spam box, because maybe the email is there. We send the email with the access link a few hours and 15 minutes before the webinar. So check your account. If you don't find the email, you can register again, and then you will get a new access link. So Felix, if you want to make your final remarks, then we're going to finish this second day.
Yeah, thank you, Eduardo, again for organizing the professional training. So it has been a great pleasure today to present. So today we have been looking more on the signal aspects and what does this infer to the estimation of the parameters. Tomorrow we are going to look into signal acquisition and parameter tracking, which is the parameter estimation process of the signal parameters, time delay, phase, and Doppler. And then I will hand over to the colleagues from the UPC, and they will continue with what you do with these estimates. So I hope you have a great day today, and we'll meet together. We meet again tomorrow for the second part of the signal processing part of the training. I'm having a lot of fun presenting, and I hope we have also more questions. Don't be shy asking more questions. All the questions are good questions. Don't worry. It's not easy to follow. I think there's a lot of math also involved, and if you have questions, and if it's if all the questions can help to make it more clear also to the others if we discuss things again. So keep up, maybe writing more questions tomorrow, and more also comments. I'm also happy receiving comments how to improve things or to explain things better. So have a great afternoon and see you tomorrow.
Hey, thank you, Felix. On behalf of Galileo Information Center Brazil, we like to thank everyone for participating in this second day of the professional training. Thanks also to the speaker, Dr. Felix, for your presence and your time to prepare the presentation, deliver the lecture, and answer the questions. And maybe Adria do you have a few words to give, Adria?
No, it was a very interesting day today. I think everyone has learned a lot about the signals and all of the methods in this tracking that Felix was presenting, and let's wait for tomorrow. Thanks everyone for connecting.
Okay, thank you everyone. We remind you that the materials are already available for you to download from the event's website. We await everyone's presence tomorrow for the third day of our professional training at the same time. Okay, see you tomorrow.
See you.
Bye.
Bye-bye.
Bye.